Assalamualaikum and good day to all of you. We are still in chapter 2. We are discussing about first order differential equations. In this section 2.2, we are going to discuss linear equations. Definition 2.5. A first order linear differential equation is an equation of the form dy dx plus p of x times y equals q of x, where p and q are continuous functions over an interval I. Okay, so this equation is of first order, where y is the dependent variable and x is the independent variable. Now this equation is said to be linear in y. It is linear because it has satisfied all the criteria for linearity. Notice that y is to the power of 1, dy dx is to the power of 1. The coefficients of dy dx and y does not involve any function in y, and at the same time p and q are functions which involve x alone. Therefore, it is guaranteed that there won't be any non-linear function in y. Okay, so we say that this is a first order linear differential equation, or you can say it is a first order linear equation in y, where y is the dependent variable. Now, an equation that is written in the above form is said to be in standard form. When we say standard form, it means that the coefficient of dy dx is 1. Okay, so if the coefficient of dy dx is equal to 1, then this equation is considered as a standard linear equation. Now look at the function q of x. When the q of x is equal to 0, the linear equation is said to be homogeneous, otherwise it is non-homogeneous. Okay, now for linear equation, it can either be homogeneous. Now when we say homogeneous, it means the function q of x is exactly equal to 0, because this part is equal to 0, and it is non-homogeneous if the q of x is not equal to 0. Okay, so a linear equation can be homogeneous, it can also be non-homogeneous. This term homogeneous, when we say linear homogeneous, it is not the same as the homogeneous equation which we have discussed in 2.1. Okay, so in 2.1 we have discussed an equation known as a homogeneous equation, but this time the word homogeneous refers to the linear equation where the qx is equal to 0. Okay, so don't get confused between this word homogeneous in this section 2.2 and the homogeneous equation which is discussed in 2.1. Okay, so this is the standard form of the first order linear differential equation, dy dx plus p of xy equals to q of x. So suppose we have an equation which is written in this form, dy dx plus x squared y equals to 0. Okay, so this is dy dx plus, now p of x in this case is given as x squared, multiplied by y equals to 0. The q of x is equal to 0. So we say that this is a first order homogeneous, because the q of x equal to 0, linear differential equation. And this equation is in standard form because the coefficient of dy dx is 1. For the second example, dy dx plus x squared y equal to sine 3x. Again, this is a first order equation and it is linear, but we call this equation as non-homogeneous because the function q of x is not equals to 0. Procedure for solving linear equations. Let us now learn how to solve a linear equation by executing the following steps. The first step is to ensure that the given linear equation is in standard form, which is given by dy dx plus p of x times y equals to q of x. The second step is to identify p of x. Now what is p of x? P of x is the function which is the coefficient of y. Now what do we do with this p of x? We want to evaluate the integrating factor, which is denoted by mu of x. Mu of x has this formula, it is equals to e to the power of the integral of p of x dx. Okay, so we substitute p of x into this integrand, evaluate the integral which is the power of this e. The next step is to multiply both sides of the standard linear equation by mu of x. Okay, so multiply the first term on the left side of the equation by mu of x, so we get mu of x dy dx. Multiply the second term on the left side of the equation by mu of x, so we get mu of x times p of x y, And on the right side of the equation, multiply mu of x with that function given here. So on the right side, we get mu of x times q of x. Now once this is done, take note that the left side of the equation can be converted into the derivative of a product of mu of x and y. So whatever is written on the left side of the equation, no matter how complicated it looks, it is actually equivalent to d dx of the dependent variable multiplied by the integrating factor. Now how do we know that these two are equivalent? So let's show that these two are actually equivalent. We start by looking at the derivative of the dependent variable and the integrating factor, mu of x. Now by definition, we know that mu of x is equals to e to the integral of p of x dx. So let us evaluate the derivative. Take note that this is a product of two functions, u, v. So when we differentiate u, v with respect to x, we know the formula is u, v prime plus v, u prime. Okay, so we get the following. This is equals to u is y, and v prime, evaluate the derivative respect to x of this exponential function. So the answer is p of x e to the integral of p of x dx. This is u, and this whole thing is the v prime, plus v, okay, this is v, multiplied by u prime. U prime is the derivative of y respect to x, which is dy dx. Okay, so this is the derivative of this given product of functions after applying product rule of differentiation. Now we know that e to the integral of px dx is mu of x, so change this into mu of x. So we get y p of x mu of x plus mu of x dy dx. Rearrange this term, okay, put this to the front. So you get mu of x dy dx plus, and this bring it to the second term, we get mu of x times p of x times y. So notice that this expression is the same as that, the same as the one on the left side of this equation, and this expression is equal to this, which is exactly this one here. Because this shows that the expression on the left side of this equation is exactly equals to the derivative of the product of the dependent variable and the integrating factor. Okay, the next step is to integrate both sides of the equation. So we integrate the left side with respect to x, we integrate the right side with respect to x to get the unknown function y. So y is equals to 1 over the integrating factor multiplied by the integration of mu of x, q of x with respect to x plus a c. Okay, so these are the basic steps that we need to follow, that we need to apply in order to get the solution for a given standard linear equation. Now let us start solving some problems. Find the general solution of the given linear differential equation. So in this first question, we are given the equation y prime plus 3x squared y equals to x squared. Now take note that y is the dependent variable, and this equation is linear in y, because y and y prime, they are both to the power of 1, and the coefficients do not involve y or its derivatives, and there is no non-linear function in y existing in the equation. So this is a linear equation. In fact, it is a standard linear equation because the coefficient of dy dx, or the coefficient of y prime, in this given problem is 1. Okay, now we're going to start solving this standard linear equation by firstly identifying p of x. Now p of x is the coefficient of y. In this problem, p of x is 3x squared. Evaluate the integrating factor, which is given by e to the power of integral of p of x dx. Okay, now substitute 3x squared into p of x. So we need to find e to the power of the integral 3x squared with respect to x. The integration of 3x squared with respect to x is x cubed, and therefore mu of x is e to the power of x cubed. The next step is to multiply the standard linear equation by the integrating factor, which is e to the power of x cubed. Okay, so the first term multiplied by e to the power of x cubed gives e to the power of x cubed y prime, plus the second term also multiplied by e to the power of x cubed gives us 3x squared y times e to the power of x cubed, and on the right hand side we get x squared times e to the power of x cubed. Okay, so the left side as well as the right side of the standard linear equation has been multiplied by the integrating factor. Notice that the left hand side of this equation can be rewritten as follows. The left hand side of the equation is actually equivalent to d dx of the product of the dependent variable and its integrating factor, that is d dx of y times e to the power of x cubed. Okay, if you differentiate this product of functions with respect to x using product rule of differentiation, uv will get u v prime plus v u prime. Okay, so this expression is equals to this expression. Now we shall continue to find the unknown y, but firstly we have to eliminate the derivative d dx. And to do so, we integrate the left hand side with respect to x, and we do the same for the right hand side. Okay, so integrate the left hand side with respect to x. When we integrate the derivative of the function with respect to x by fundamental theorem of calculus, it gives back the function itself. Okay, so the integration of the derivative of ye to the power of x cubed with respect to x gives back this function, so the answer is ye to the power of x cubed. And on the right side, we need to evaluate the integration of x squared e to the power of x cubed with respect to x using the technique of substitution, where we let u equals to x cubed, and therefore du will be 3x squared dx. This implies that x squared dx is du over 3. Okay, now apply the appropriate substitution. Ye to the power of x cubed is equals to, now x squared dx now being replaced by du over 3, and e to the power of x cubed now becomes e to the power of u. Now integration of e to the power of u is still e to the power of u, and therefore ye to the power of x cubed is equals to 1/3 e to the power of u plus a constant c. Resubstitute u as x cubed, and therefore ye to the power of x cubed is 1/3 e to the power of x cubed plus a c. So finally we can write down the general solution, or we can express y explicitly in terms of x. So the answer is y is equals to 1/3 plus ce to the power of negative x cubed. In this second question, we are given an equation given by x divided dx equals to x cubed minus x plus 4y. Now this equation is a first order linear equation, but it is not given in standard form. Okay, the standard linear equation is given by dy dx plus p of xy equals to q of x. And notice that the function involving p of xy is written on the left side of this equation, and therefore we need to shift the 4y to the left side of the equation. So we do the following: x divided dx minus 4y. Okay, after shifting 4y to the left, we get this is equals to x cubed minus x. Next step is to ensure that the coefficient of dy dx is 1, and that can be done by dividing the whole equation by x. So we get dy dx minus 4 over xy is equals to x squared minus 1. So this is now the standard linear equation, okay, where y is the dependent variable. So we can proceed by solving this standard linear equation by identifying the p of x. Okay, now p of x is given by negative 4 over x. Okay, p of x is the coefficient of y. Substitute p of x in the formula for the integrating factor, e to the integral of p of x dx. Now p of x is negative 4 over x dx. Evaluation of this integral, integration of negative 4 over x dx gives negative 4 ln x, and we know from the formula e to the a ln b is the same as b to the power of a, and therefore e to the negative 4 ln x is the same as x to the power of negative 4. Next step is to multiply the standard linear equation by the integrating factor. Okay, so we multiply the first term dy dx by x to the negative 4. So you get x to the negative 4 times dy dx. And for the second term also multiply by the integrating factor. So the second term is negative 4 over x, y, x to the power of negative 4. And on the right side, multiply by the integrating factor. So x squared minus 1 multiplied by x to the power of negative 4. Now the left side of this equation can be rewritten as d dx of the product of the dependent variable and the integrating factor. Okay, so d dx of y x to the negative 4. This expression here is equivalent to this expression. When you apply product rule of differentiation, uv, you get uv prime plus v u prime. Okay. After this, we want to solve for y. We integrate the left hand side respect to x and we integrate the right hand side respect to x. But when we evaluate the integration of the derivative of this function with respect to x, we'll get back this function. So on the left side, we get yx to the power of negative 4, and the right side, integrate x to the power of negative 2 minus x to the negative 4 with respect to x. And we integrate the right side. Integration of x to the negative 2 gives negative x to the power of negative 1. Integration of negative x to the negative 4 gives plus x to the power of negative 3 over 3 plus a c. And lastly, we write down the general solution. Or in other words, we express y explicitly in terms of x. The result is y equals to negative x cubed plus x over 3 plus cx to the power of 4. The third question, x plus 1 times y prime plus x plus 2 times y equals 2x e to the power of negative x. Now this equation is linear in y, but it is not in the standard form because the coefficient of dy dx or the coefficient of y prime is not 1. So to make it in standard form, we have to divide this whole equation by this factor x plus 1 to get y prime plus x plus 2 divided by x plus 1 times y equals to 2x e to the power of negative x divided by x plus 1. So this is now the standard linear equation. Notice that the p of x, which is the coefficient of y, is given by x plus 2 divided by x plus 1. Okay, use this p of x into the formula for the integrating factor. So integrating factor mu of x is equals to e to the power of the integral p of x dx, which is e to the power of the integral x plus 2 over x plus 1 respect to x. Now this quotient involves a numerator which has the same degree as the degree of the denominator, and therefore we are going to do division to re-express this in a different form. Now x plus 2 divided by x plus 1, by division we get 1 and the remainder is 1. So x plus 2 over x plus 1 can be re-expressed as 1 plus 1 divided by x plus 1. Okay, so 1 plus 1 divided by x plus 1. Integrate 1 with respect to x gives x, and integrate 1 over x plus 1 with respect to x gives ln of absolute x plus 1. By the law of exponent, e to the power of a plus b is e to the power of a times e to the power of b. And therefore e to the power of x plus ln of absolute x plus 1 is the same as e to the power of x times e to the power of ln of absolute x plus 1. But we know that e to the power of ln a is a, and therefore e to the ln of absolute x plus 1 is simply x plus 1, and then multiply by e to the power of x. So this is the result of the integrating factor. Mu of x is e to the power of x times x plus 1. Multiply the standard linear equation by the integrating factor. So the first term we get y prime multiplied by the integrating factor e to the power of x times x plus 1. For the second term, x plus 2 over x plus 1 y multiplied by the integrating factor. On the right hand side, 2x e to the negative x over x plus 1 multiplied by the integrating factor. Now the left hand side may look a bit complicated, but actually the whole expression is equivalent to d dx of the product of the dependent variable and the integrating factor. And on the right hand side, when we simplify, we can cancel the factor x plus 1. We can also cancel the exponential function. So what is left on the right hand side is just the function 2x. To eliminate the derivative, on the left hand side, we integrate the derivative with respect to x so that we get back the given function. So on the left hand side, we get y e to the power of x times x plus 1, and on the right hand side, integrate 2x with respect to x, and we get the answer as x squared plus a c. And finally, we can write down the general solution where we express y explicitly in terms of x. We get y is equals to x squared divided by e to the power of x times x plus 1 plus c divided by e to the power of x times x plus 1. In this subsection 2.2.2, we are going to learn about another type of first-order differential equation known as a Bernoulli equation. A Bernoulli equation is given in the following form: dy dx plus p of xy equals q of x y to the power of n, where n is not 0 and n is not 1. Due to the fact that n is not 0 and n is not 1, this Bernoulli equation is considered as a non-linear differential equation. However, a Bernoulli equation can be transformed into a linear equation by using an appropriate substitution. So now let us learn how to solve a Bernoulli equation. Given the standard Bernoulli equation, dy dx plus p of xy equals q of x y to the power of n, where n is not 0 and n is not 1. So let's call this as equation number 1. We start by dividing each term by y to the power of n. Okay, so divide each term by y to the power of n to get as follows: 1 over y to the power of n dy dx plus p of x y divided by y to the power of n is equals to q of x. Okay, now let's call this as equation number 2. Now let u equals y divided by y to the power of n. Okay, so this factor here, y over y to the power of n, we shall call it as a u. Or we can also say u is equals to y to the power of 1 minus n. Okay, call this as number 3. Differentiate the left hand side with respect to x, and so when you differentiate the left hand side with respect to x, we get du dx, and on the right side differentiate with respect to x, you get 1 minus n multiplied by y to the power of, now 1 minus n minus 1 multiplied by dy dx. In other words, du dx is equals to 1 minus n y to the power of negative n dy dx. Okay, now du dx is 1 minus n. Now y to the power of negative n is the same as 1 over y to the power of n dy dx. In other words, 1 over y to the power of n dy dx is equals to, now bring this 1 minus n factor to the left, is equals to 1 over 1 minus n du dx. So swap the position of these two. This implies that 1 over y to the power of n dy dx is equals to 1 over 1 minus n du dx. What does this tell us? It tells us that this number 4, the expression in number 4, which is this part here, can be replaced with 1 over 1 minus n du dx. So this part here will be replaced by this expression, whereas y over y to the power of n will be replaced by u. So this is the standard Bernoulli equation, which in the previous slide we have labeled it as equation number 1. And we divide this equation by y to the power of n to get equation number 2. And we define y over y to the power of n as u, or u equals to y to the power of 1 minus n. And in the previous slide, we have shown that 1 over y to the power of n dy dx is equals to 1 over 1 minus n du dx, which we call as equation number 4. So what we are going to do now is to substitute 3 and 4 into equation number 2. Okay, so this is equation number 2. 1 over y to the power of n dy dx plus p of x y divided by y to the power of n equals to q of x. Now, since we are going to substitute 3 and 4 into equation number 2, so the new equation will be as follows. Now 1 over y to the power of n dy dx will be replaced by 1 over 1 minus n du dx. And y over y to the power of n will be replaced by u. So the new equation that we are obtaining is in the form of 1 over 1 minus n du dx plus p of x u equals q of x, and this equation will be labeled as equation number 5. Now take note that this equation number 5 is a linear equation where u is the dependent variable. Okay, so it is linear in u, and once you've got the linear equation in u, we have to solve the linear equation, and finally, before we get to the final solution, we need to resubstitute u as equals to 1 to the y to the power of 1 minus n. Example, solve the given Bernoulli equation by using an appropriate substitution. Dy dx plus y equals to y cubed. Now this equation matches the standard form of the Bernoulli equation. Okay, dy dx plus p of xy, in this case p of x is 1, is equals to q of x is also 1, y to the power of n, y cubed. So in this case, n is equals to 3. So 3 is not 0, 3 is not 1, and therefore this equation is a Bernoulli equation which is non-linear because the power of y is not 1. So we're going to solve this Bernoulli equation by dividing the whole equation by y cubed. So we get 1 over y cubed dy dx plus y over y cubed equals to 1. Okay, let's call this as number 1. We define u as y over y cubed. In other words, u is equals to y to the power of negative 2. Okay, let's call this as number 2. Differentiate u with respect to x to get du dx. So when we differentiate u with respect to x, we also differentiate y to the negative 2 with respect to x, which gives us negative 2y to the power of negative 3 dy dx. Now bring negative 2 to the left side, so that y to the negative 3 dy dx is equals to negative a half du dx. Now call this as number 3. The next step is to substitute 2 and 3 into equation number 1. Okay, so take note that 1 over y cubed dy dx, which is this one here, can now be replaced by minus a half du dx. So this term will become minus a half du dx plus, now y over y cubed has been defined as u. So plus u equals to 1. So notice that we are getting an equation which is linear in u. Okay, u is the dependent variable, and this equation is linear in u because it fulfills the criteria of linearity, where u and du dx, they are both to the power of 1, and the coefficients do not involve the dependent variable u or its derivatives, and there are no nonlinear functions in terms of u existing in the equation, and therefore this is a linear equation in u. So what we have seen is that from the Bernoulli, it now has been transformed to a linear equation after we have performed the appropriate substitution. So next step is to solve this linear equation. Now this is a non-standard linear equation because the coefficient of du dx is not 1. So first step, make it in a standard form, multiply everything by negative 2, so we get du dx minus 2u equals to negative 2. Okay, evaluate the integrating factor, which is e to the integral of p of x dx. In this case, p of x is the coefficient of u, which is equals to negative 2. So e to the integral of negative 2 dx, which is the same as e power of negative 2x. Okay, so this is the integrating factor, mu of x. And we know that after this, we have to multiply the standard linear equation by the integrating factor. Now the left hand side, after we have multiplied by the integrating factor, is the same as g dx of the product of the dependent variable. In this case, the dependent variable is u with the integrating factor. Okay, so d dx u e to the negative 2x, and on the right hand side we also multiply it with the integrating factor and continue to solve this equation. U e to the negative 2x is equals to negative 2 times the integration of e to the minus 2x with respect to x, so we get e to the negative 2x plus a c. In other words, u is equals to 1 plus ce to the power of 2x. But we know that u is y to the power of negative 2 based on our substitution. Okay, so u equals to y to the negative 2, and therefore the solution for this Bernoulli equation is given in the form of y to the negative 2 is equals to 1 plus ce to the power of 2x. Okay, so this is the solution of the Bernoulli equation. Now take note that we have solve this equation by differentiating u with respect to x to get number 3. Now we can also use the formula that we have discussed in the previous slide. Okay, now instead of going through these steps, we can simply replace this term by using this formula. Okay, 1 over y to the power of n dy dx equals to 1 over 1 minus n du dx, and we know that n is equal to 3. So 1 over 1 minus 3 du dx is the same as 1 over negative 2 du dx. So if you have memorized this formula, okay, you can immediately replace this term here by negative a half du dx, and so you don't have to perform these steps at all. Okay, provided you have already memorized this formula. Second equation, x squared dy dx minus x cubed y to the power of negative 1 is equals to xy. Let us compare this equation with the standard Bernoulli, which is given by dy dx plus p of xy equals q of x y to the power of n, where n is not 0 and n is not 1. Okay, now notice that p of xy in the standard Bernoulli lies on the left side of the equation. However, for this problem, p of xy lies on the right side of the equation, and q of x y to the power of n in the standard Bernoulli lies on the right side of the equation, whereas in this problem, q of x y to the power of n lies on the left side of the equation. And we also notice that the coefficient of dy dx is not 1. So let us rearrange the terms and divide by x squared to get the standard form of the Bernoulli equation. So the first step is to swap the position of these two functions. So we get x squared dy dx minus xy equals x cubed y to the power of negative 1. After this, we divide the whole equation by x squared to get the standard form of the Bernoulli equation, dy dx minus 1 over xy equals xy to the power of negative 1. Okay, so this is n is equals to negative 1. So let us proceed to solve this standard Bernoulli equation by dividing the whole equation by y to the power of negative 1. So 1 over y to the negative 1 dy dx minus 1 over x y divided by y to the power of negative 1 equals to x. So 1 over y to the negative 1 is the same as y over y to the power of negative 1 is the same as y squared. Okay, define u as y squared, so that du dx is 2y dy dx. Therefore, y dy dx is the same as a half du dx. Okay, bring 2 to the left side. So that means y dy dx, which appears in this equation, can now be replaced by a half du dx, and y squared can be replaced by u. Okay, so this is the substitution. Half du dx, which is this term, minus 1 over x u is equals to x. Okay, now we are getting a linear equation in u. U is the dependent variable. So the Bernoulli equation has been transformed to a linear equation after we have made this substitution. Okay, now we are going to solve this linear equation, but firstly you must make it in standard form by multiplying the whole equation by 2. So du dx minus 2 over xu equals to 2x, and the p of x is the coefficient of u, which is negative 2 over x. Evaluate the integrating factor, we get x to the power of negative 2, and multiply the standard linear equation by this integrating factor, and so the left side is exactly equals to d dx of the product of the dependent variable u with the integrating factor And on the right side, we multiply 2x with x power of negative 2, resulting in 2x power of negative 1. Now ux power of negative 2 is the integration of the function on the right with respect to x, which gives 2 ln of absolute x plus a c, and therefore u is equals to 2x squared ln of absolute x plus cx squared. But we know that u is equals to y squared, and therefore we need to replace u by y squared. So y squared is equals to 2x squared ln of absolute x plus cx squared. So this is the solution for the given Bernoulli equation. Okay, so we have already shown the steps of the solution, where we get the solution by using this substitution. But actually there's another method that we can use. Instead of using the substitution, we can use the formula 1 over y to the power of n dy dx is equals to 1 over 1 minus n du dx. In other words, once we have reached this step, we can immediately change this 1 over y to the negative 1 dy dx. Okay, replace n by 1 to get this form 1 over 1 minus negative 1 du dx, which is 1 over 2 du dx. So once we have reached this step, replace this term using this formula, which becomes a half du dx, and then minus 1 over x, and replace this by a u equals to x. So alternatively, we can simply apply this formula. From this step, we can straight away go to this step. Okay, we can avoid using this substitution. Alright, so this is the end of today's lesson. We have already discussed two types of equations. One is linear equation and the other is Bernoulli equation. We can solve the Bernoulli equation by transforming it to a linear equation using an appropriate substitution. Thank you.